Hello, everyone. Matthew Cruz here. I'm really excited to share with you the things I've been learning about writing high performance F sharp code. And I'm going to tell you ahead of time, this is going to be a little rough. I'm going to be doing these all in one take. I'm not going to be doing lots of editing afterwards, in part because I want to take you on the experience of what it's like to diagnose and benchmark and figure out what's fast and what's slow, but also because I just don't have the time to do lots of editing. So this might not be as polished as what some other people have done. But I want to get the content out there because it's stuff I haven't found enough of. And I'm guessing I'm not the only F sharp developer interested in this. So today, what I'm going to do is I'm going to be looking at a very kind of small little problem that came up during my work and just kind of do some exploration around different approaches that I could take and what the performance implications are. And I want to take you on that journey with me. So you're gonna see it from very raw. So there might be mistakes along the way. I might get lost, but we'll get through it and we'll figure it out. So whenever I get these performance questions, I'm like, oh man, would it be faster to do A? Would it be faster to do B? I always like to create just the most simple benchmark possible that kind of illustrates the problem and then come at it from a bunch of different angles. And in this case, the problem that I was dealing with is that we have an algorithm that is basically part of the most inner loop of our simulation engine. And as a part of that, what we have to do is at times we need to look up a value by a coordinate pair. So I have two integers, and that pair represents a coordinate. And I need to look up like a flow associated with that pairing. And to do that, there's a bunch of different ways you can model that in F sharp. So let's get into some code and I kind of show you the different thoughts that I had and kind of discuss with you the possible pros and cons of different ones. And so what I've done here is I have this empty directory. I named it dictionary lookup of coordinate pair. And I can just do a dir to see, hey, there's nothing in here. So what I'm going to do is I'm going to do a .NET new console, and I'm going to have the language be F sharp. Oh, .NET new. Yeah, see, this is raw and unedited. You're getting me actually failing at this. There we go. And now I'm opening up. I'm going to just do code into that. So now I'm opening VS Code in that directory, and let me drag it over to this folder and let me zoom in for you so you can see what's going on here. So in this directory, I get my program.fs, and some things I'm going to have to do right off the bat in order to do some benchmarking is I need to come into the FS proj file, and I'm going to need to add some things in here. And one of the first things that I do, and I'm cheating a little bit. I'm copying and pasting from another project because I've done this so many times that I'm like, okay, I'm just going to just do it. First thing I do is I say, hey, I'm only really concerned about the x64 platform. So this is something that's really important. All of the benchmarks that I do based on compiling for x64. Because again, for the work that I do, we always have to use x64. We don't target 30, like any PC, 32-bit, and that's for some restrictions for other components in it. It's beyond the scope of what discussing here, but what's important to know when you're doing benchmarking, the platform can really matter. So what I'm doing here is only going to apply for x64. If you're dealing with any PC or like a 32-bit, go ahead and take this code, change this restriction to target any PC or the 32-bit, and see what the difference is. So be very mindful of that because you can see some wildly different things. The other thing that I'm copying and pasting in here is I'm adding some references to the benchmark.net library. And so now I'm going to make this available. So if you're using like JetBrains Writer, which I love, or using Visual Studio, which is another fantastic IDE, you probably can do this all by just like right-clicking somewhere and saying manage NuGet packages. For this benchmarking stuff, I know exactly what I want to do. I don't need the IDE to really like help me out. So I use VS Code. But I'm going to come back here. I'm going to say, hey, .NET restore, just to make sure that those libraries are installed. So I should be good to go now. So just, I'm just alt-tabbing between these windows. So the other problem here is that benchmark.net as a library is really authored with C# in mind. C# is a great language. I have no hate for C#, but that means you're going to have to do some things that might be a little funky for F#, but to kind of deal with the fact that benchmark.net was really written from a C# developer's mindset. But fortunately, those things are not that big a deal. The main thing that will have to trip you up is I almost always end up doing this, where I'm going to just, again, kind of copy and paste, is I create my entry point here. And I am also going to just go ahead and grab a bunch of these things that I'm probably going to use. This is saying like, hey, I wanted to open up these libraries and I'm going to be using them. Benchmark.runner is the code that allows us to, we're going to define a class which holds our benchmarks. And I almost always call it benchmarks because I'm really creative like that. And if we want to have what we're going to do is we add methods to it. And those methods are the things that benchmark.net are actually going to be profiling. So Ember here, test, and it's not even going to do anything. But if I want benchmark.net to actually run this thing repeatedly to test it, what I do, test. There we go. What am I missing here? I believe that should be fine, but it's not. Again, this is what I have read. Oh, it's not test. Benchmark. Too many unit tests. Too many unit tests today. So what this annotation, this attribute that I put on this method is telling benchmark.net is like, hey, this is a method that I want you to profile. So what it will do is it'll take that and it'll run it a whole bunch of times to get good statistics around the performance of that method. It's really important to use benchmark.net and not kind of roll your own with timing because it's really easy to fool yourself. And there's a whole lot of gotchas. If you want to know more about that, I recommend, again, this is why I write stuff down. So on my blog, Matthew, so I have a page here just called Fast F#. And this is where I kind of put the essentials, pro.net benchmarking. This book is fantastic, and it kind of goes into all the details of why benchmarking is hard and why you should use a library for doing it. And Andre Atkinson, I believe, he's like the primary author, one of the main authors on benchmark.net. So don't write your own profiler, go use another's. And it's relatively easy. I hope by the end of this, you're going to see like, oh, that wasn't so bad. So our question was, the question we wanted to answer is most performant, it's kind of vague. Fastest way to look up a value for two ints. And I'm going to just go ahead and annotate, say it's int32. So there's a bunch of different ways to model this. And the simplest way is just the humble tuple, right? So you could say, hey, I'll go ahead and close this since that's all we need to see here. So easiest way is say like, hey, I'm going to have my pair just be, 1 and 2, right? So what this is saying in the type annotation is like, hey, this is a tuple, an F# tuple. And right now that tuple is a 2-element tuple. And those values are 1 and 2. So you could say like, hey, I'm just going to use the built-in F# tuple. Really easy and straightforward. Okay, you could do that. And honestly, and this is another big caveat, I am very much writing F# code from the perspective of high performance. This is not what I would be doing is if I was a part of a team doing a suite of microservices or something like that. The code is different. The use case is different. So F-sharp's defaults are great. And if you just go with them, 9 times out of 10, you're going to be absolutely fine. I am assuming that you are interested in writing really, really fast code, and you really want to understand all the different knobs and dials that you can turn to get the most possible speed out of F#. So that's the audience that I'm assuming. This is not a, what is the best domain-driven design way of doing this? I'm not that guy. There are other people much better than me than that. I'm the, how do I make this go as absolutely fast as flipping possible? That's what I'm about. But those two things aren't actually at odds, but that's where I'm focusing right now. So there's another way, there's another type of tuple in F#, and it's the struct tuple. And so I'm going to say struct pair, and I'm going to say struct of 1, 2. So this kind of looks the same, but it also looks different. And so if you're new to F# and you're not aware of this difference, there's something really important going on here. The default tuple in F# is a reference type. That means it's allocated on the heap. A struct pair, a struct tuple, is allocated on the stack. So this thing will not cause garbage collection when it's created. Whereas this tuple, the default, the ref tuple, will. So I'm going to kind of keep being clear when if I say just tuple, I'm talking about the default tuple in F#. It's a ref tuple. If I'm talking about a struct tuple, I'm going to specify struct tuple because it's not the default. Struct tuples are what C#'s default is. And so if you want to be API compatible with C#, you use the struct tuple. There's a lot of times, so I'll just stop there. So performance considerations right here. Hey, how much is GC killing me, right? If your algorithm just like runs once a day, like do not care about this. You probably don't need to care about this. If it's running all the time and you're some server situation and you're wanting to reduce the amount of garbage collection that's happening, consider using the struct tuple. It's not that much more work, and you're going to get lower GC pressure. Another way that you consider modeling it is as a record, right? So you can say, hey, I'm going to have pair record, and I'm going to just define this type. I'm going to say like, hey, I have an X, that's an int, and I have a Y, and that is also an int. This, what's interesting about this is, again, you're dealing with the fact that F# records are ref types, they're reference types. So again, this is going to be allocated on the heap, not on the stack. What you can do is there's a few different ways to define structs in F#, which I found a little bit confusing. And so I'm trying to develop a better terminology around this. So I'm going to add this annotation typed struct pair record and X int Y int. Okay. So you notice here, I put this annotation on this record definition here. What this is doing is it's telling the F# compiler that we want this thing to be laid out and treated like a struct. It's still a record, so you can still use kind of the with syntax. So if I went ahead and said, hey, let chicken equal x equals 1, y equals 1, right? And if I want to say like, hey, I want chicken 2, let chicken 2 equal chicken with y equal to 10. So we can still just because this has now been annotated with a struct, you can still use this really nice syntax for like, hey, take the old one, but like update a field on it. You can still do that. The key thing is that how these things are laid out in memory are different. Normal F-sharp record is a reference type and it's allocated on the heap. A struct, a record with the struct attribute is allocated on the stack. What's important to note is often people think of things that are allocated on the heap as F-sharp records have structural equality. So they're kind of, I'm not saying you can think of them as value types, but you kind of can. And like what people mean when they say value type, reference type, struct, that all kind of gets murky. For me, what I get primarily concerned about is where is this thing in memory? Because that's primarily what I care about. What incantation I use to get it where I want it to be, that can vary. So that's something to really consider here. So I want to just kind of consider these scenarios here just to start off, because like this would be what I would absolutely start with. There's some other like crazier things that we might explore later, but let's get through this. So what I'm going to do now is I've defined, well, these are built in, so I don't need to define those. But what I'm going to do is I'm going to create a dictionary and I'm going to put the same sets of keys and values in each of them, except in one dictionary. I'm going to go ahead and define them. Right. So I'm going to have my default tuple dictionary. I'm going to say it's a dictionary, and this thing's key is going to be int, and the value inside of it is going to be a float, just for kicks and giggles, just so it like looks a little bit different. So here we're saying, hey, we got a dictionary. The type of the key is going to be the int tuple, and the value inside of it is going to be a float. Doesn't really matter what it is, but here we go. So then we have struct tuple dict, and that's going to be another dictionary. And this is going to be struct int float. Now I'm writing out these type signatures here just so it's very clear like what these are. The compiler would infer these once I started using them, but I'm just trying to be like, I'm overly defining things for you so you can see clearly what's going on. So this is how you would say, hey, this thing's key, it's a struct tuple, and the types are int. And again, the value is a float. So then other type is going to be, I'm going to call default record dict. It's going to be a dictionary, and it's going to be a pair record float. Right on. Cool. It's happy. So the keys in this one are going to be of this type. And then we have struct record dict dictionary, struct record float. There we go. So these are the 4 different dictionaries I'm going to test against. Now what I need to do is I need to generate some random data that I'm going to insert in them. So one of the other things that's really important when creating reproducible tests. Oh, I'm sorry. My night thing is kicking in. Let me just turn that off here in a second. Okay. I don't want the color on the screen to get funky for you. So when generating random data, it's best to system.random, and I'm going to give it a seed of 1, 2, 3. And this means every time it starts up, system is not required. Every time it creates a random, you can let it just arbitrarily choose a random key to start the random number generation, or you can give it one, and that way you're going to get the same values every time. When I'm doing these benchmarks, I always set that seed value to make sure that if I run the test repeatedly, I'm going to be testing the same values. so that like I want it to be reproducible. I don't want to get like randomly different things just because the random numbers are different every single time. That would be obnoxious. So what I'm going to do now is I'm going to generate the random data I'm going to put into these dictionaries. So let random keys and values. So I'm going to say, hey, let, I want to restrict like the key range a little bit. And so I want those X and Y values to like not be like arbitrary ints or whatever. So max key value, I'm going to say is 100. And let max value is going to be 100. So this is going to be the max value that I'm going to be putting here into these floats. So random keys and values, and let number of pairs. I'm going to say 1,000. I don't know, just kind of picking something. Well, I'm going to go with 100 because, again, I'm primarily concerned about a very particular use case I have in mind. And I'm trying to choose restrictions that means I'm testing in the domain of values and numbers that I actually care about. I don't necessarily care about crazy wacko things. I don't care about infinities or something like that. So I'm restricting down to the space that I care about. So number of possible pairs for this domain be about 100. So what I'm going to do is I'm going to generate 100 of these. What's the best way to do that? Someone's probably going to come in later and dunk on me and show like a more efficient way to do this, but this is just kind of how I do it. So for 1, 2 number of pairs, I'm going to say, yeah, okay. I'm going to generate a random X, I'm going to generate a random Y, and I'm just going to generate a random value. I'm going to put in that. So I'm going to say, hey, let X equal number generator next, and it's going to be, and the max value I'm here is max key value. And I will just point out that the max value is exclusive to the upper bound. So we're generating between 0 and 99 are the values that we could possibly be generating in this case. So let Y equal random next, max key value, and let value, I'm just going to say V. I'll just put value. Next double. And the thing about this one is next double just generates something between 0 and 1. And if I want it to be in here, I just need to take that whole thing and multiply it by my max value. So now value is going to be something between 0 and 100. And from there, I need to create some key value. Well, what I'm going to do is I'm creating this data set, and then I'm going to populate these dictionaries with this data set. I'll have to do some different things. So X, Y, and value. If I wanted to, okay, I'm going to be a little cute. I'm going to use an anonymous type. So key is going to be equal to that, and value is going to be equal to that. All right. So that's just to make things a little bit easier for me. This is just an anonymous type declaration in F#. So from there, now we need to populate each of these. So I am going to be lazy and just use some I'm going to do some for loops. Yeah, but I'm in a class, and so I'm going to have to use do, I believe. So do for X, Y value in, you know what, for key and value. Random keys and values. You got to do this. Well, let's see if it works successfully first before I tell you. So for this first one, we're actually going to populate them all at the same time. So default tuple dict, we say like, hey, I want you to do key and value and key. And that's going to be equal to key and value. And so what I'm doing there is I'm saying, hey, for this key in this dictionary, put this value in there. And for the struct tuple dict, I need this thing to be a struct. Okay, I kind of hurt myself a little bit with here. So I'm going to undo this a little bit. I made things too complicated on myself, so my apologies. But again, this is free. So there you go. So X, Y value. So what I'm going to do now is saying, hey, X, Y. And this is just going to be value. So I'm looping through all these. For the default tuple dict, I'm just using the default tuple, the reference type tuple, and I'm putting this value there. And then for struct tuple dict, I am going struct X, Y, and value. Yep. For the default record dict, if I want to put something in there, I'm going to be a little lazy. And oh no. Nope, can't do it. So let default record pair. I'm gonna have to do this. It's all good. It is all good. Equals, and X is equal to X, Y is equal to Y. So the reason I'm having to do this, I'm annotating saying like, hey, what this type is because the compiler in F#, structurally, these look the same. They both have X and Y fields of type int. And so if I just did this, it would say, hey, this is a struct pair record, because what's happening is the compiler is just going up. The compiler is just going up the line. It's like, what's the first type I see, which looks like this? And the first one it finds is the struct pair record. But I want to create a pair record, so I have to do an annotation there so that it actually gives me what I want. So now I can populate. I'm going to separate these. Populate this with that default record pair, value in it. And then I'm going to do the same thing for struct record pair. In this case, I don't have to do the type annotation, but I'm going to, because I'm trying to be considerate of people who haven't been doing F# as much. So this is not strictly necessary because the F# compiler, because the F# compiler would see this kind of structure. This is the first thing it would find, and it would find the one that we're actually looking for. But I'm trying to have some symmetry here so it's easier to follow. But by struct record dict, here we go. Struct record pair, and we'll put value in there. So now what I've done is I randomly generated some keys and values, some X, Y pairs and a value to go with it. And then I iterated through all of them and I populated the different dictionaries. Separate this out. Populate the different dictionaries so they all have the same values, right? Now what I need to do is I want to generate a whole bunch of random keys that I'm going to loop through in my benchmark and see what the performance is. Now to do that, I'm going to get random keys. And so let me think about the best way to do this. So I need to get the keys out of here, right? So what I'm going to do, So I just realized I have made a mistake. I have to be a little careful here because I did generate 100 pairs of these, but it's possible that I generated some duplicates because I generated the same X and the same Y. And so list.distinct. Oof. Oof, 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 oof. Unique. Distinct. By first. Okay. What? Okay. I'm trying to keep this as like low on F# cons as possible. And I realize I might be just be throwing a little too many things at you. But essentially what's going on is it's looping through this entire list, but it's just looking at this first thing. And it's saying, hey, this is the thing that defines whether something is unique or not. And so this is making sure that all those random keys and values that I only have one instance of any XY pair. But now I have to change this structural match here. Okay. So we're good again. So now I know I only have, in this list of values, the keys are distinct. So that's kind of important. So I need to get the keys. So let keys equal random keys and values and list.map first. First is a function, like 2-element tuples are so common in F# and generally in functional programming that there's these two functions called FST first and second SND. And so we're just getting the first element of a 2-element tuple or the second element of a 2-element tuple. So here I just went through and I'm grabbing all the keys. I'm going to turn this into an array of list because I'm going to be like randomly jumping around and like grabbing values in here. And it's fine. So this kind of makes me a little bit annoyed because okay, I'm just going to let it play. I'm going to let it play for now. So I got these keys, all the keys in this random array, and then I want to say how many different lookups do I want to perform in a given loop. So let number of lookups. And so in this case, I'm going to do 1,000 lookups. So I now want to do is I want to create an array. So for in 0, so 1 to number of lookups. Let's do. So this is like an array expression and say, hey, I'm going to iterate through the values of 1 all the way up through number of lookups, and I'm just going to randomly select a key. Again, and so keys, random number generator, next, and I'm going to give it an upper value of keys.length. So what's going to happen here is it's for the values 1 to number of lookups. I'm going to generate a random number from 0 to the length of the array. But remember, next is exclusive on the upper bound. So I'm not going to like go too far outside of the array. And I'm just going to get a random value from the keys. Now I just have this random set of 1,000 keys that I'm going to look up and test out. So here we go. I think we're ready to create some benchmarks. Now I've set up my data. It's reproducible. I can change the dimensionality of stuff if I want. So here we go. So I'm going to default tuple is going to be my first test. And so what I'm going to do here is something to consider is the .NET compiler is really, really, really smart. And it will do everything it possibly can to eliminate dead code or unnecessary work. So I'm going to use what is I call an accumulator in here, make it mutable so that the compiler can't figure out I'm not actually doing anything with this value. So it's like forced to do the work. So let mutable equal 0.0. And I'm going to say, hey, for I equal to 0 to random keys dot length -1 do. And what I'm gonna have this thing return the accumulator at the end. I'm gonna say, hey, accumulator. So next key, and yeah, random keys. Go get, because now what I'm doing is I'm gonna iterate through the random keys array, and I want to get the key that's in that spot, and then I'm going to go do the lookup in the dictionary. Okay, default tuple dictionary. Okay, so I got a key. This is a random one. Default tuple dict, and I'm going to look up the next key. And I'm going to say, hey, accumulator is equal to accumulator plus whatever value is in there. Right? So I'm going to click. Okay, and I'm back. I might have to take just like random pause breaks. So here we are. What we're doing, and this is something that you might be asking, hey, Matthew, why aren't you just using like the for I, like, you might say like, hey, Matthew, why don't you use for I in random keys do? I could do that. That's going to use an IEnumerable. That's going to cause a little bit of overhead, just the allocations. And I try to create a benchmark where I like remove as many confounding factors as possible. And that's why I have random keys as an array, and I'm going in order because I'm giving the CPU the best possible chance of like knowing what data it's going to need ahead of time. This is the only place where I want there to be anything that's like unpredictable, because this is the thing I'm actually testing. So that's why I use a for loop. It's why I am going linearly through an array. I'm not jumping around, so that getting the next value it needs to use in this lookup here is as predictable as possible for the CPU, so that I'm trying to isolate the behavior that I'm wanting to mess with. Now, I made a slight mistake here. I have the random keys, but these random keys are the normal tuple, but I need struct tuple, and I need my two different record types. So I'm going to have to create 3 more different arrays with keys in the correct structure, because again, I don't want to measure the performance of like, hey, taking this tuple and then turning it into the key and then going and doing the lookup. I purely want to say like, you have a key, look up the value. How fast is that? Now you might admit, like I mentioned here, I have this mutable accumulator that I'm using here, and I'm doing some work with it, and then I'm returning it at the end. This is to make sure that the generated code is actually doing the lookups, because if I didn't do anything, I just said, hey, 0, or even like unit, the CLR is insanely smart, and it would say like, wait a minute, this method, like you call it with unit, you do some stuff, but then you just return unit. It would just eliminate this code. It's like, no, there's no point for me even doing it, because like you don't do anything with it later in the program, which is why I often use this pattern of having some kind of accumulator and doing something with it to convince the compiler to convince the CLR, like, yes, I really do need you to do this work. Otherwise, it wouldn't do it, and like stuff would just be instantaneous, which would be great, but doesn't actually give us the knowledge that we're wanting. So I'm going to rename this not random keys, but random tuple keys. So it's more clear what's going on there. And now I need my let random struct tuple keys. Now, what's important is that I've generated random data, but I want to test all these different dictionaries having to do the same work. So I want it to like functionally have to look up the same data, but it has to be in a different structure. In this case, I need a struct tuple, not the ref tuple. So now what I do is I take this, take my random tuple keys, and I'm going to do an array.map on that thing. And I have x, y, and I'm going to say, hey, now turn that into struct tuple for me. So now these are the keys that I'm going to use for testing in the struct tuple dictionary. And while we're here, we might as well do this for the other ones. So let random pair record keys. I'm gonna double check that's what I called it. Pair record struct. Yep, cool. Yay me. Random tuple keys. Array.map function xy. And remember that we have two different records. One's a ref one, one's a struct. And right now the compiler is just going to match against the first one. So we have to say like, no, we actually want this one. Easiest way I know of doing that is pair record x equal to x and then y equal to y. And so, normally you could just define a record doing that, but you see, hey, it thinks it's a struct pair record. By prepending that first field name with the name of the record type, this is my way of telling the compiler like, hey, it's actually a this. And it's like, cool. So random struct pair record keys. Oh my gosh, these are some long names. Somewhere some developer is angry. X, Y, and now, and again, if I just do x equal x, y equal y, it's going to figure out that it's a struct pair record, which is what I want because it's the first thing it would find by going up the file. But again, for the sake of symmetry, struct pair record, not part of the reason I'm doing that, like, well, I would never have two different records with like the same, okay, I'll take that back. It would be extraordinarily unusual for me to have two records with like the same fields defined in the same place. But it could happen. And so in code that you would write and that you put in a service and you knew that that phenomenon was going on, I would recommend being explicit about this, that like, hey, this is a pair record and this is a struct pair record, because at some point someone could do a refactor and move this thing down. And now the compiler is giving you a different result because you've switched the order. And so the type inference is doing something different. So when in doubt, be clear, I guess is how I would say it. So, but now we've created the arrays of the different keys that we need. So here we go. So this is going to be another benchmark, and remember, this is struct tuple, and let mutable accumulator equal 0.0, I equals 0 to random struct tuple keys length -1 do. Let next key equal random struct keys I. Accumulator equals accumulator plus struct tuple dictionary. Next key. and then be sure to return it. Otherwise, the compiler, the CLR will say like, that doesn't even do work. I'm not even going to do it. Member, and then now we're doing pair record. And let mutable. Here we go again. 0, 1, 0. Whoop, for I equal to 0, 2. Yeah. Random pair keys length is 1 do. Let next key equal random pair keys I. Accumulator equal accumulator plus pair record. Where did I call it? What did I call it? Okay. Key. Oh, don't. That'd be hilarious. That'd be like the most confusing loop structure ever. Like, don't do this. Oh, okay. Benchmark member struct record. Let mutable accumulator. Yeah, you get in the picture. For I equal 0 to random struct. Length is 1. Do. Yep. Let next key equal random struct pair record keys I. Accumulator struct predict next key accumulator. Cool. So there we go. We now have 4 benchmarks where we're going to go through and look at what the performance is on what is the same X and Y pairs, but just stored in memory in different ways. Ooh. Ooh. Oh no. I just realized something. Oh, dang. How to make this fair? So here's the tough thing. I just I realized, because these keys are shoot. So you know how like you have the reference tuples and the struct tuples? Struct tuples, like when you iterate through this array, that struct tuple is going to be right there in the array. It's not going to be like a reference to an object somewhere else. And so the struct ones automatically have a huge advantage, well, potentially have a big advantage. Let's see what the performance difference is between these, and we can go back. This might be a good thing to investigate what's going on. Okay, this might be good. Okay, I was going to go ahead and run this thing. So I'm going to come back over here. I'm going to say .NET run configuration release. And so this is me saying, hey, I want you to run the project and I want you to use a configuration release. If you don't do this, benchmark.net will say like, hey, I'm not going to benchmark debug code. So no. Let's see if I made a bug. Should be interesting. Starting up. Compilation stuff. So what you see at the beginning is that in order to have these benchmarks be meaningful, the CLR has a lot of rules around like what stuff does it, how hard does it try to compile it or optimize it? And then there are rules based on like how many times you run it that will determine that. So, and I know I'm glossing over a lot of details. Again, read the .NET benchmarking book and you'll get a whole lot more information about what's going on in there. But you have to run it a bunch of times in order to kind of get a stable result, because the first time you do it, basically just measuring how fast the CLR is like compiling the stuff to your local So yeah, that's why you have to do a bunch of repeated measures, and that's why you should use someone else's library and not your own for measuring this stuff. So this will take a little bit. I'm going to let this run. I'm going to go back and talk about the thing that I'm concerned about. So we have these arrays. We're iterating through the arrays to get the key, the next key that we want to look up. The problem is the struct ones. Structs are their value types. And so when you have an array of them, they're just there in the array. And so when you iterate through it and like, hey, I need this value, and it's right there. With the default tuple, which is a reference type, and the default record, they're both reference types. So what's in the array is not actually the thing itself. It is a reference to where it is in the heap. So as we are iterating through these things, we are kind of doing slightly two different things. In one case, we are just getting the value and doing the lookup. In one case, we're like getting a reference and then having to follow the reference to get the thing that we want to look up. Ew. That's kind of annoying. So I'm not sure the best way to address that at the moment. I'll probably reach out to the community and say like, hey, what's the way to kind of get around this limitation? Because I'm trying to isolate the behavior I'm most interested in, which is looking up something in a dictionary. And right now I'm kind of confounding it a little bit, because there's the difference between these tests isn't just what you're using to look up in the dictionary. It's also difference in like going and getting the thing that you need to look up, which is kind of annoying. So, and also since we're doing 1,000 of them, it's taking a little bit while for these benchmarks to actually run. Which one are we on now? We're on that was the default tuple. So we've gotten through one. Oh, we're done. Cool. So let's look at what we see here. Let's zoom in for you. Nice. And so you get some basic specs on the machine that you're looking at. And what we're seeing, SDK 601. This is what's important to me is like, hey, I targeted x64 fault job. Not sure why that's saying debug. It's kind of scaring me a little bit. But here we are. We got the tuple, the default tuple, so the reference tuple took 126 microseconds to look up 1,000. So it's iterating through the arrays, doing it 1,000 different lookups. And this is taking 126 microseconds. The struct tuple took 24 microseconds. The pair record took 17.83, and the struct record took 17. Pretty smoking fast. So I think I'm going to call it here for the day, but you can kind of see the takeaway is like, that's interesting. Struct record and pair record appear to be kind of the same, very close. And you see how like, okay, like this is like, because the error here, like 0.8 microseconds, 0.3, like this is, when I look at this, I say like, this is essentially the same. What's going to be interesting later is to kind of dig into this a little bit more, what's going on, because what we do know is difference about this is the array that we're iterating through to get the key. In one case, it had to follow a reference to get that record. In the other case, the record was right there in the array. So this slight difference, again, this error is like, the standard deviation. Okay, I'm not even going to say that, because we look at these standard deviations, like if we did like some statistical, like the student t-test, and okay, statistically, these are essentially the same. That's what I'm just going to say. There's not that big of a difference here, but there might be some implications that we can look into later on and how to speed this up even more and go a little bit faster. So I'm going to leave that for next time as a follow-up, because I'm going to try to keep these to a reasonable amount of time. But hopefully you saw like, hey, it's pretty quick to create benchmarks, and it's pretty easy to see like, hey, there's a difference in performance of these things and different ways you could be approaching the problem. So Till next time, thank you very much, and I hope you enjoy. Bye.